Okay, hello. So today I'm going to be taking you back in time to question the life and ultimately the death of one of the most fearsome predators we've ever known in our oceans. I'm of course talking about Megalodon. So this fearsome shark, some estimates have placed it as growing up to 60 feet in length. It had teeth the size of your hand. This isn't a really small person's hand. It really did grow teeth absolutely huge. And it's thought they could have possibly even swallowed a small car whole. These had a huge, huge bite to them. And although there's kind of all this interest out there, there's all this fascination in the species, there still remains very little information out there, but real scientific information on what this species ate, what it, or why it died, kind of how it lived. And that's what I'm going to try and answer today. So just to run you through an outline of this talk, I'm going to go through the hypothesized causes of Megalodon's extinction, its interaction with the great white shark, and then go through my methodologies, which are novel to this study, the results and conclusions. So let's get started. So there are two leading hypotheses behind the extinction of Megalodon. The first of these is climate change at the end of the Pliocene. The second of these is that the evolution of a large predator caused dietary competition with Megalodon and ultimately led to its extinction. And it's this hypothesis here, the competition with the great white shark, which I'm going to be testing today. So how do the great white shark and Megalodon relate to each other? So the great white shark evolved around the Miocene-Pliocene boundary back here. It's a little bit sketchy as to the exact time periods, but you do tend to see a gradual transition through leading up to the great white shark. And the presence of great white shark's teeth in sedimentary deposits is kind of iconic of the Pliocene. So they really are pretty much a Pliocene starting fish. When you get to Megalodon, they are incredibly common throughout the Miocene, and then as soon as you hit that Miocene-Pliocene boundary, you actually start to see a decline in the species. They're still around, and they actually go extinct right towards the end of the Pliocene, which is why climate change has been brought into question. But you do see this decline in the abundance of fossil shark's teeth of this species from the early Pliocene onwards. And that is where the competition between the great white shark comes into play. So now we know a bit about theories, we know a bit about the history of these two species. What are the questions I'm actually answering? So the first of these is whether there is direct dietary competition between the great white shark and Megalodon. And if that's the case, whether this competition led to the extinction of Megalodon itself. So if this was the case, you'd expect to see a shift in Megalodon's diet after the evolution of the great white shark. So we know our questions, we know our species. The big problem now is how we're actually going to analyse this. So stomach contents isn't really an option in fossil sharks. Well, not in these species anyway, there just isn't enough data. Tooth morphology has been used to infer that these species ate the same thing, but because the teeth are pretty much the same shape, but just in different magnitudes of size, this can't really tell us that much more. So that came to microware. So at Leicester, we study a 3D microtexture analysis approach on a whole range of species, where we take the initial tooth, we take a mould and a cast, run it through this microscope here, an infinite focus microscope, which produces a 3D surface of the tooth, which looks kind of like this here. It's great, you can spin it around, it's brilliant fun. But the problem with this is, this incorporates sort of the tooth's morphology as well. So it's only a tiny section, but there's still going to be gross morphology of that tooth surface. So we run it through a whole series of polynomials and filters and levelling processes, which take out that morphology of the tooth and just leave a flattened surface with just the roughness texture from that tooth surface. And that's the part that we're really interested in, is the roughness. So from this data set here, we run it through more mathematical equations and clever bits of software, and it puts this whole surface into a numerical context. It summarises it into 22 different parameters of roughness. And we end up with a giant data table that looks like this and gives you a headache. The problem with microware, though, is that this has never been tested before in sharks. This is a completely novel approach. So we do it in Leicester on other different animal groups, but sharks wasn't, to this point, an option. And you have to ask yourself, because sharks shed their teeth, is microware going to be a viable option for testing microware? Is there enough time for a roughness signal to build up on a tooth before the teeth are shed? So So to test this, we had to go back to modern sharks, so bear with me for a bit, we are talking modern. So I've used the sand tiger shark. This is a species which is common in aquaria across the country, and the importance of this is it has a very controlled diet. So aquarium sand tigers eat fish, and chunks of fish at that, usually don't even eat whole fish. Whereas when you start to look at the global distribution of wild sand tigers, so that's all the yellow points, there's kind of a range of dietary data out there, some better than others. But from North America, where we focus this study, there are quite a few studies which have shown that as sand tigers increase in size in the wild, they eat a large proportion of sharks and rays in their diet alongside their fish. So in theory, if microware works, if you compare captive sand tigers which are eating only fish to wild sand tigers off the coast of North America which eat sharks and rays and fish, there should be a clear separation between the two. And this is exactly what we see. So the yellow points, just over here, are our fish eaters, our captive sand tigers, and our green points are sand tigers of varying size caught off the coast of North America. And as you can see, there is a very clear trend from pure fish eaters up to elasmobranch brown eating sharks. There's this separation between fish and fish eaters, captive and wild, which is really good. And for those people out there who like the statistics, just point out that the principal component one is actually separating the data. It's showing incorporating 97% of the variance within this data set. So it really is a good separation along principal component one. And if that hadn't convinced you enough, if you rank in each of the individuals based on the proportion of sharks and rays you expect to see in their diet in comparison to fish, and plot those against the principal component 1 scores, you see a really clear correlation between wild sharks with an increasing elasmobranch proportion to principal components 1, and an incredibly significant p-value as well. So microware really does work on sharks. Yay. But you're not here to hear about modern sharks, you're here to hear about Megalodon. So for this part of the study, I've taken samples of Megalodon and great white teeth from across the Miocene and the Pliocene. So these are different localities found within Florida. For the later localities, I made sure that there were Megalodon and great white samples found within the same fossil horizons. So from this we have to assume that they were cohabiting the same environments at the same times. These early points here, there are other large macro predators around, but obviously no great whites, they hadn't evolved yet. So we applied the same methodologies as before, and these are just a reminder of the 2 questions that I'm actually asking, whether there's competition between the 2, and whether there's a change in Megalodon's diet, and whether this is indicative of a causation of extinction. So, does Megalodon's diet change through time? Short answer to that is no. So, again, we've got principal component scores, and this is from the fossil locations. This is like a summarised time period for each of them. And you can see that although there's a slight wiggle, this line really doesn't change. It stays fairly horizontal as time goes on. And then to the next question of, is there dietary competition? So these next few slides basically summarise the principal component scores for each of these species through time. So we start off with the Miocene. This is Megalodon. We can see simplified principal components runs along this sort of time scale, this sort of range. And again, we've got a very high principal component score along here. As you move to the Miocene-Pliocene boundary and you see the evolution of the great white shark, you see that the great white shark results fit incredibly nicely right in the centre of Megalodon's dietary range. So the really short answer to this is there's really strong dietary competition between these 2 species. And as we move on to the Pliocene, unfortunately I don't have any data for the great white sharks here. There were great white sharks teeth present, but due to the preservation of the teeth, I wasn't able to collect data from them. We can see again that the range of Megalodon really hasn't changed. And if we just summarise these here, we can see that from the Miocene going down through to the Pliocene, although there is a small shift at the Miocene-Pliocene boundary, this isn't significant. So there is no change in Megalodon's diet through time, And also, we know that from this plot here, there is very strong dietary competition between the two. So what can we conclude from all of this? So microware can be used to distinguish dieting sharks. It's the first time this has been shown. It has high importance for not just fossil work, but also for modern conservation work of sharks. That great whites and Megalodon did eat the same food items. There was a high level of dietary competition between the two. But because Megalodon's diet didn't change through the last 13 million years of its existence, we can fairly safely say that dietary competition with the great white shark wasn't a leading cause of the extinction with Megalodon. Please want to thank a few people, funding from Palace to help me go across to America, but also from various different museums and people for their specimens as well. And possibly anyone's got any questions?